Hello everybody. So now we're going to talk about the calculation of enthalpy difference for mixtures. And we mean by mixtures that we are not dealing with a pure component. For all the previous cases and all the previous problems that we solved, we started or we're dealing with a pure compound that is being heated or cooled, either when we're talking about steam in chapter 7 or in this chapter that we had only pure components. So if we have a mixture, then the enthalpy can be calculated using different equations based on the type of system. The case that we are dealing with here is the ideal case. The ideal case means that the enthalpy of the mixture is equal to the enthalpy of individual components, which is not the case for all the mixtures. For example, if you add water to acid, to HCl or to H2SO4, then if you are doing this in a test tube that you are holding with your hand, you will feel the heat. There is heat that's generated due to mixing the two components. This, of course, this is not an ideal case. This heat is because of formation of new bonds of interaction between molecules, which is a very non-ideal case. And in this case, we should take into account what we call the enthalpy of mixing, and this is a very long topic that is out of the scope of this course. So there are there's I think a couple of pages in the textbook that is dealing with the ideal mixtures or non-ideal mixtures and the heat of mixing. We're not going to cover it here in this videos, but it's there in the textbook if you're interested, and you'll find more information in the thermodynamic textbooks about this as well. But anyways, the case that we're dealing with is the ideal case where we can calculate the Cp of the mixture as using this equation. It's the summation of the mole fraction multiplied by the Cp of each one of the individual components. So if I have n number of components, then I is the component 1, 2, 3 up to n, where n is the number of components in the mixture. So it's the mole fraction of the first multiplied by the Cp of the first. The Cp is constant plus constant multiplied by T plus constant multiplied by T squared plus constant multiplied by T power 3. This is the most common form that we deal with. And this is what you would see here, that we have 1 subscript 1 for these to represent the constants for the first component, and then we have the same for the second. You can do the same for third and fourth up to the last component in the mixture. And by doing this, you can get the enthalpy difference for the mixture between temperatures T1 and T2 using the integration. In this case, this Cp of the mixture represents the whole mixture. You don't need to do the calculations for each one of them separately now. You're just dealing with the whole mixture. So it's Cp mixture of T, dt from T1 to T2. And this can be, if you substitute with this formula here, you can take the coefficients of T power 0 or take it as a common factor, and then take the coefficients for T power 2 together to T power 3 together, and so on. There is a missing plus here. I'll add it here. Or this is repeated term. So yeah, I think I did a mistake here. This is a repeated term. So it's T power 2, T power 3, and T power 4. So I think I repeated this by mistake. Anyways, so this is what you will end up with. It's exactly the same calculation that we do for the delta H for a pure component, but the only difference is the constants. This is what you are going to make in a different way. Of course, this is valid if you have the same limits of integration, or you have the same reference state and you are calculating the temperature at the same temperature, or the enthalpy at the same temperature for all the components. If you have different components with different reference states, you can calculate delta H for each one of them separately, and then get the delta H of the mixture. Of course, this is the hat, which means that is the specific. So delta H hat of the mixture equals delta H hat of each one of the components multiplied by Yi. And we said before that the enthalpy difference is independent on the reference state. So you can calculate each one of the delta H's of the components separately using a different reference state, and then get the delta H of the mixture using this relation. But this relation is only valid, this one, under the condition of having the same reference state. We will see in next video, inshallah, a case where we will have different reference states, which is going to be very helpful. But what we have here is just a very systematic approach that we can follow in order to calculate or do the calculations for what we call a single phase system. A single phase system, we mean by it that we have no phase change. I want to remind you that we listed the cases where we can calculate the enthalpy difference. We said the first, if pressure is changing at constant temperature and phase, and then the temperature is changing at constant pressure and phase, and third, the phase is changing at constant temperature and pressure. So when I mean single phase, I mean that there is no change in the phase. So there might be change in pressure and there might be change in temperature. So what the steps that we have here are going to be like kind of repeatable, repeated things that we already discussed before. So we had the energy balance equation, we simplify it, put the terms that are equal to zero equal zero. And then we check if we want to calculate delta U or delta H, whether it's an open or a closed system. And for the enthalpy change, we can get delta H using either tabulated data, using the steam tables or the enthalpy tables like table B8 that we discussed before, or you can do this by integration of the CPDT or CVDT, depending on the type of change that we have or the type of system. And we will calculate the enthalpy of mixture if we have a mixture, and then we substitute and calculate the missing terms. So it's a very systematic approach, so it's not adding much to what we have been doing before. But let's take this example where we have a mixture of methane and air. It's 10% methane and 90% air by volume. By volume is the same as by moles, so both is in gas phase, of course. It's to be heated from 20 degrees Celsius to 300 degrees Celsius, and we want to calculate the heat required to heat this mixture from 20 to 300 in kilowatts if the flow rate of the gas is 2000 liters per minute, and the 2000 liters between brackets is STP. STP is the standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere. So if under these conditions I want to calculate the heat input in kilowatts, let's first use this information of the 2000 liters. So the 2000 liters per minute is the volumetric flow rate. We have volumetric flow rate, and in our problems that we do the calculations for, we use molar flow rate because we have the specific enthalpy calculated in kilojoules per mole. So I want to make this 2000 liters, convert this into molar flow rate. So this is gas phase under one atmospheric pressure. So this is the pressure. So we can use the ideal gas law to calculate the molar flow rate from N equals PV over RT. I'm putting here the pressure in atmosphere, the volume or volumetric flow rate in liters per minute. So R must be 0.082 because R equals 0.082 liters atmosphere divided by mole Kelvin. So the units must be homogeneous. The temperature is in Kelvin, so we can calculate this. The product would be in mole per minute, of course, and this is the molar flow rate. Now let's go to the first step, which is the calculation of the writing the equation. So the equation is will end up to be Q equals delta H. There is no work, there is no change in kinetic or potential energies, so Q equals delta H, which is N dot multiplied by delta H hat. This is the shape that we saw before, so it's N dot multiplied by H2 hat minus H1 hat. N dot is already calculated here, so we need to get this delta H, which is H2 hat minus H1 hat. This is for a mixture of methane and air, so we will calculate the CP of the mixture according to the relation y multiplied by Cp plus y multiplied by Cp. We already got the constants here. There is one thing that is I need to discuss here, which is the I put here the values that we have in the tables for the constants for the two gases, for air and methane. We discussed the air before, and we said that air is one of the components in the table, so we don't need to break it into oxygen and nitrogen. So we know the molecular weight. We know this is all for gas phase. This is form number one. So the equation that we know. You have the option to use Celsius or Kelvin, but if you're using Celsius for one of them, you have to use Celsius for the other. You have to unify the units. So I picked the constants for Celsius. This is 34.3 times 10 power minus 3. Don't forget the powers that we have here. And then I added 0.9 to the multiplied by the constants of air. And then this is the Cp of the mixture. I got the coefficients of T power 0 together, the coefficients of T power 1 together, T power 2 together, and T power 3 together. And finally, the equation is what you see here. This is the equation after doing the integration and substituting with the limits of integration, and then we can calculate delta H to be 8.69 kilojoules per mole. You can substitute in the equation. We know N dash or N dot is 89.3. We know delta H is 8.69. So this is going to be in kilojoules per minute, which can be converted into kilojoules per second. So this is what we want to calculate, which is the heat. There is one other thing that we can do here, which is repeating the solution without doing the Cp of the mixture. So I can say that the delta H is delta H of methane plus delta H of air. I know the total number of moles, so I can get the number of moles of methane from the mole fraction, the number of moles of air from the mole fraction, and I will calculate delta H of each one of them separately. So this is the integration of Cp dt from 20 to 300 for the constants of methane, and then I'll do the same for air. Of course, you will notice here that the integration, I did the integration twice. So the step that I did before once, I am doing twice because I'm doing once for air and once for methane, and then when you substitute, you will get the same, the exact same results. So this is important just to give you an idea that it doesn't matter which one of the methods that you're using. Either you're using, and if I go back to the to this slide here, either you're going to go with this equation or you are going to use this equation. Both will give the same results. But of course, this is going to be more time consuming because you are doing the integration twice. In the first solution, you are doing the integration once. So this is all for this video. Next time we will discuss another problem, which is a very, very important one. So I'll talk about this next time. So I'll see you then.